Question 6 or question 16 from the higher/intermediate paper, looking at the probability question. So here it is, the probability question. So you can see it's about how you get to the top of Snowdon, whether we've got male or female, walking or taking the train, and we're asked to look at this tree diagram. So before we get too far into this question, actually what we're going to do is we're going to look at tree diagrams. We're going to look at whether events are independent and unpick that to start with. Let's look at how we combine outcomes or events. So we've got two simple rules we can follow, and the or rule. So first of all, let's have a look at and. If we are combining different events, so in this case I am going to flip a coin and roll a dice at the same time. So the outcome I'm interested in is getting heads on the coin and a 5 on the dice. So the rule is, if I want heads and 5, I do the probability of a head times by the probability of getting a 5, and I just multiply them. So chance of the probability of getting a head is a half, probability of getting a 5 is a sixth. If I multiply them, I get 1/12. Let's look at a different situation. We've got Wales playing a game of rugby and the school playing a game of rugby. The probability that Wales win is 1 in 3, and the probability the school wins is 2 in 5. I'll put those in a table. My question is, what's the probability that Wales win and the school wins? So probability that Wales win needs to be times by the probability that the school wins. So that's a third times 2/5, which gives me 2/15. So that's the and rule, one thing and another, and we multiply them together. We have a look at the or rule. So let's have a look at the or rule now. And I'm going to do the same two situations. Well, I'm going to look at just rolling a die on its own, and I'm interested in what's the probability of getting a number which is a multiple of 3 when I roll this dice. So the only two outcomes I'm interested in are 3 and 6, and I know that the probability of getting a 3 is a 6, the probability of getting a 6 is a 6, and because of this or situation, I'm interested in 3 or 6. I add the two together. So this is the other rule. If it's an or situation, I add my two probabilities together, and I can simplify that to get my final answer of a third. If we look at the rugby example where we've got Wales winning or the school winning, I've just worked out all the 4 possible options there. So Wales win and the school win is 2/15. Wales don't win and the school wins was 4/15. Wales win and the school doesn't win 3/15. And neither team win was 6/15. And they were all worked out using the previous and rule. But in this particular question, I'm asked what's the probability that at least one team wins. So the outcome I'm interested in is just that one team has won. It doesn't matter which team. So in fact, there's 3 ways we could achieve this. Either Wales win and the school win, so that's one way. Wales don't win and the school wins. Or Wales win and the school doesn't win. So there's 3 possible situations that I need to put together. Now, because it could be the first one or the second one or the third one, either of these meet the criteria, I add the probabilities. So the chances that Wales win and the school wins 2/15. Wales don't win and the school win 4/15. Wales win and the school doesn't win 3/15. And I get, when I add those together, 9/15. You might be able to spot another way that you could work that out looking at the 6/15 and the 9/15, but if you can't, don't worry. What you need to remember is if it's one thing or the other or another, we add our probabilities together. Okay, so let's have a look at a tree diagram and what it tells us. It's a way of planning out what's going on. So we're going to use these in 2 different situations, independent or dependent, and that affects a couple of things, and we'll see what's going on. So the first situation is on my journey to school. If I catch the school bus, there are 3 different colour buses that could turn up: the red bus, the yellow bus, or the green bus. Now, once I've ridden the bus, I have to get off and walk into school, and I can either be late or not late. And that happens whether I get the red bus, the yellow bus, or the green bus. So I can either ride the red bus and be late, the red bus and not be late, the yellow bus and be late, yellow bus not late, green, late, green and not late. So you can see you've got these 6 different outcomes that could happen when you're getting the bus turns up, you get on it, and you can either be late or not late. If we have a look at this second tree diagram, this is where I've got a choice of whether I could get on the bus, I could walk, or I could take the car. And again, if I get the bus, there's still a chance I could be late or not be late. If I walk, there's a chance I could be late or not late, and the same with the car. So I've got these 6 options still. My method of transport, whether I'm late or not late. Let's now put some numbers on these branches. So there's obviously more red buses in the depot because there's a 50% chance of a red bus turning up, 40% chance of a yellow bus turning up, and a 10% chance of a green bus turning up. Regardless of what colour bus turns up, there's a 20% or a 0.2 chance of being late, 80% or 0.8 chance of not being late. And this is what we call an independent. And it's independent because the chance of me being late doesn't change depending on the colour of the bus. So whether a red, a yellow or a green bus turns up doesn't make any difference to me being late or not being late. Okay, if we have a look at the probabilities on this bus, walk, car option, my decision making process in the morning, I'm more favour the bus, 30% chance I'll walk, or the 0.1 chance I will take the car. And depending on that, if I take the bus, there is only a 10% chance of me being late and 90% or a 0.9 chance that I'm not late. But if I walk, it's 50-50. If I take the car, 0.6 chance of being late, 0.4 chance. So these late and not late probabilities change depending on whether I take the bus, I walk, or I use the car. So my late, not late probabilities depend on my method of transport. So this is a dependent event. The probabilities change for the late or not late. So important things to remember as you go through this. Okay, let's have a look at this question then and see if we can use what we've just talked about. If we go along a branch and along another branch, we're going to multiply because that's going to be one event times by another. And if we combine branches, we are adding the outcomes. So let's have a look at this question and see what's going on. Just zoom in a sec. So first thing we need to fill in is our missing probabilities. Now we're told in the question we've got a 0.42 or 42% chance that the person is female, and a simple calculation, subtracting that from 1, we know there is 0.58 probability that they are male. So we're just filling in the probabilities on each branch. The next thing is we know that walking or taking the train is independent of gender. So we know it doesn't matter whether it's male or female. These things will stay the same. Walk here will be the same as walk here. Train here will be the same as train here. Let's see what else we've got. So the probability the person took the train is 0.35. So I can pop 0.35 train there, and I know it because it's independent, it's train there. It's 0.35 as well. We know the probability adds up to 1. So 1 minus 0.35. Probability of walking must be 0.65, whether you're male or female. Part B on this question then, a person is chosen at random and receives a gift voucher. What is the probability that this person is female and travelled up the mountain by train? So what we want to do is we want to follow a route through on our little tree diagram. I want a female person that took the train. So I want these two events to be combined. So I want the probability that they're female and they took the train. I know that means I need to do the probability they're female times the probability they took the train. So probability of 0.42 times the probability of 0.35, and I would strongly recommend popping that in your calculator so it's calculator paper, 0.147. And that's it. Now as your alternative question, I'm going to do a dependent probability tree question. That takes a bit more working out, so it's quite a good question because it's going to show you lots of different things you can do with the probability tree, so just worth having a watch. I've got a fruit bowl, I'm going to take 2 bits of fruit out, there's 5 apples, 2 pears, and then I'm asked to look at the probability I have 2 different items of fruit, 2 items of fruit that are the same, and that I've got at least 1 apple. So 3 things to do after, but the first thing I need to do is draw out my tree diagram. So I know there's 7 items in my bowl of fruit, and I could either take an apple or a pear to start with. There's 5 apples, so it's 5 out of 7, and there's 2 pears, so 2 out of 7. And then I take another bit of fruit, so I could either have taken an apple to start with, and then I go back to my fruit bowl and take another item. But the reason this red box has popped up is because my second choice depends on what I had to start with. If I've taken one item already, I've only got 6 items left, so my probabilities are now going to be out of 6. And if I took an apple to start with, I still could take another apple, or I could end up with a pear. Equally, if I took a pear to start with, I could have an apple and then a pear as my second options. So let's look at the probabilities for those. We know they're going to be out of 6 because I've already taken one bit of fruit. But if the probability of taking another apple, if I started with 5 apples and I've already taken one, I've only got 4 apples left. Okay, if I picked an apple first, I haven't eaten any pears, I've still got 2 pears left in my bowl, so I've got 2/6 of a chance of getting a pear. If I took a pear to begin with, I haven't touched any apples, so there's still 5 apples out of the 6 items of fruit. If I took a pear to begin with, there must only be 1 pear left out of all 6 items of fruit. And now I've got 4 different things that could happen. I could go along the top branches, so I could have an apple and an apple. And we know if it's an and situation, I multiply these probabilities together. I could go apple first and then a pear, so that would be 5/7 times 2/6. I could go a pear and then an apple, so 2/7 times 5/6. Or I could go pear and pear, so 2/7 times 1/6. And we'd need to work out all our fractions and multiply those together, and you can do that in your own time. So that's planning out all the different things that could happen. Okay, now let's put this together then and answer parts A, B and C. So A is the probability they're different, B, probability they're the same, and C was the probability that we have at least 1 apple. So for different options, we could have picked an apple first and a pear second, or could have picked a pear first and an apple second. So I don't need both of these things to happen. I want one thing or the other thing to happen. Either I have an apple and pear, or pear and an apple. Because it's the OR rule, we know that that means we actually need to add these 2 things together. So apple and pear is the black 5 out of 21 plus the blue 5 out of 21, giving us 10 out of 21. Probability that they're the same then for part B is apple and apple or pear and pear. So I know I need to add apple and apple is 10 out of 21 in the orange, pear and pear 1 out of 21 in the purple. So we get 11 out of 21. The last bit then, at least 1 apple. So there's 3 ways you could end up with at least 1 apple. Apple and apple, pear and apple, or apple and pear. And again, it's an OR situation, so we need to add those 3 together. 10 out of 21 plus 5 out of 21 plus another 5 out of 21, 20 out of 21. Also, another way you could think of this question, so you could do either method would be fine. The probability of getting at least 1 apple, the opposite of that, if you like, is 1 minus the probability of you getting no apples. Okay, 1 minus the probability of no apples is 1 minus the probability of getting 2 pears. Okay, and so in this situation it would be 1 minus 1 over 21, 20 over 21. So just remember, as you go along your branches, you're doing one thing and the other. We are multiplying, but when we combine the different probabilities, because we're looking at one option or another option, we are adding. And that's it. So a couple of things there to remember: independent and dependent, and the and on the OR rule. Make sure you've got those stashed away in your brain.